Greetings everybody. Let's take a look at homogeneous systems and the rank of a matrix. So when we talk about homogeneous systems and kind of what's going to be the quintessential thing to deal with these will be recalling what reduced row echelon form and what that gave us. So just to remind us of that, what it took to be in reduced row echelon form was that all columns consisting entirely of zeros, if we had any at all, they had to be at the bottom of the matrix. If we look from left to right for any non-zero row, then the first entry that we'll call a leading entry has to be 1 for that row. If we have two successive rows, I and I plus 1, then those not being identically 0, then the leading entry of I plus 1 has to be over to the right of the leading entry of row I. And finally, if we had a column with a leading entry that has, then all other entries in that column have to be 0. And so kind of what that gives us is we have a matrix like this that's in reduced row echelon form, that we've got all of our 0 rows at the bottom. We've got our leading elements there, there, and there. Their leading elements successively move to the right as we move down the rows. And in the columns where we do have leading elements, all of those are going to be 0 above and below from there. And so kind of what this allows us to do is, if we want to rearrange columns, which basically just means that we're kind of re-indexing the variables in the order that we're putting them, but just rearranging the columns, we can transform the matrix to something that looks like 1, 1, 0, 3, 2, 0, 0, 0, 0 kind of on top, and then our zeros on the bottom. Or really more generally, when we're doing this, that any matrix in reduced row echelon form, we can get a form where we've got an R by R identity matrix up here in the left hand corner. Then we've got some R by N minus R matrix up here in the upper right hand corner, and we've got M minus R rows across the bottom that are just identically 0. And so what we're going to be interested in doing then is looking at the kernel or the null space of matrices that have this form. So this is really just, when we talk about our homogeneous systems, we're just talking about the solutions for the matrix, whatever matrix it is, A times our vector V, giving us the 0 value. So whenever we're saying homogeneous, that's really all that we're meaning, is this the result of our equation has to be 0. Okay. So if we kind of take a matrix of this form, let's take a deeper look at really what we can get from the kernel of that. Well, if we kind of look up here at the top, we've got, these are really corresponding to our V1, V2, all the way up to VR, because this is an R by R matrix. And so if we kind of imagine what our equations are, V1 times IR plus 1, 1R plus 2, 1 up to N. So our R plus 1s, we can kind of rearrange those and solve for V1 being the negative of R of those expressions, V2 being the negative of our values for V sub R plus 1 up to N, VR being the negative of the B R plus 1s. And so we can kind of just solve our first R variables for everything over corresponding to that B matrix over on the right with our R plus 1 up to N. Now, for the R plus 1 up to N values, those can be anything that we want them to be. They can be chosen arbitrarily for those. Those are kind of our free variables, and our R variables are dependent ones. And so if we take things like v sub r plus 1 being 1, everything else being 0, v sub r plus 1 is 0, vr plus 2 is 1, everything else is 0, and so on and so on, just kind of making each one of those v sub r sub k's successively 1 and everything else 0, what that does, it gives us n minus r independent solutions for those equations. And so what we then have is that for the matrix that has this form to it, so we've got our R identity matrix, our n minus r, our r by n minus rb matrix, our 0 rows, that the dimension of the kernel that we have is just going to be equal to m minus r, so those solutions that we had down at the bottom. Now this idea of the dimension of the kernel of A is really another term that we use for that is the nullity of A. And so what we can do now is kind of define a couple of things. The row rank of a matrix is going to be the dimension of the span of the rows of A. So now here A can be any matrix that we want it to be. And so if we just look at the rows and treat those as vectors, then the span of those vectors, the dimension of that, gives us the row rank. Likewise, the column rank is going to be our space where we just take the span of the columns of A. So we treat the columns of A as vectors. We took at the span of that to get the subspace, and then we talk about the dimension of that space, and that gives us the column rank. So for this matrix that we've got, it's pretty clear that the first R rows are going to be linearly independent, because for each one of those, if we try to take linear combination of the rows, now the zeros down at the bottom don't mean anything. That doesn't help us when we're talking about dimension. And so because of these, it's the identity matrix that keeps those being linearly independent, because we can't take linear combinations and get rid of those of the rows. And so our row rank of A has to be equal to R. Okay, so that the first R columns make up the basis, and the remaining n minus R columns. So we have a total of that. So we have that the column rank of A is going to be equal to R. So now if we remember that we can write any element in the image of A as a linear combination of the columns of A, then this means that the column rank of A is equal to the dimension of the image of A. And so we've got the dimension of the kernel of A is equal to m minus r, where r was just going to be our row rank. But our row rank, r, is also going to be equal to our column rank, and so we get that the dimension of the kernel of A, so the nullity of A, is equal to m minus the dimension of the image of A. Or if we kind of rearrange those things just a little bit, that the dimension of the kernel of A plus the dimension of the image of A is equal to m. Now, because taking any matrix and transforming to the reduced row echelon form, that is an invertible matrix operation. So all of our elementary row operations, we can reverse those and go back and forth. And so that gives us an invertible matrix operation for doing that. And so if we have M being this invertible matrix times A, giving us this kind of default value that we were looking at, then multiply both sides by the inverse, then that's going to give us m inverse times 0 for that value, and we're still left, since m inverse times 0 just is 0, that the kernel is really left unchanged for that. And so the kernel of A is going to be equal to the kernel of m times A, or our reduced row echelon form times A. So the kernels are going to be the same. So if it holds for any m by n matrix A from R to the m into R to the n, that the dimension of the kernel of A is equal to m minus the row rank. And for m times A equal to this matrix R, that for W in the image of R, we have m times A V is equal to R times V, but that's W. Well, again, doing the same thing, canceling our m inverses, canceling our m's with that m inverse, we get A times V is equal to m inverse times W. And this actually gives us something that's in the image of A. And so M inverse, this matrix that takes us to reduced row echelon form, is actually gives us a linear transformation between the image of R and the image of A. And likewise, M would then give us a map from the image of A into the image of R. Now, from a previous homework problem, we know that T mapping V to W being a linear transformation with the kernel of T being 0, then the dimension of V is going to be the dimension of the image of T. And so what that's happened, since M is going to be invertible, that the kernel of M is going to be trivial, and so that means that the dimension of the image of R is equal to the dimension of the image of A, and that's still our value R. And so what this really kind of gives us, that our row rank is going to be equal to our column rank, even in general for what we've got. And so kind of put this together for any matrix A, mapping R to the m to R to the n. So A is an m by n matrix, that the dimension of the kernel of A is equal to m minus the dimension of the image. Or kind of rearranging both of those, we get that the dimension of the kernel plus the dimension of the image is equal to the dimension of the domain space in which we start. And this theorem is actually what is known as the rank-nullity theorem. So this kind of gives us a little bit of a notion of what we mean by ranks when we talk about row ranks, column ranks, kind of how those are related, how the kernel end up relating to the dimension of the kernel, the dimension of the image, and the dimension of the space in which we start. And so later on we can start talking about projections and orthogonal subspaces and those kinds of things. Then we'll see that those have an even bigger structure from that. And so I will talk to you guys next time, and I will see you then.